Hi, welcome everyone. My name is Liam Moore. I'm the moderator for today's talk. Um, I'm very excited to announce that this talk will be about the snowplow problem, and I'm excited to welcome our speaker, Mr. Ryan Pietropaolo from the North Carolina School of Science and Mathematics. So, Ryan, whenever you're ready,
Great, thank you,
excited
Liam.
to hear your talk.
Let me just tell you a minute about the course I teach, and then we'll jump into the problem. First of all, as Liam pointed out, I teach at the North Carolina School of Science and Mathematics. We're a high school, just 11th and 12th graders. And I've been teaching this differential equations course for a number of years. Oftentimes, we have students that come in who have already taken calculus during their sophomore year of high school, and they've taken the AP curriculum. So this is kind of a nice capstone course where we get to kind of do all the fun problems that they didn't get to do in their calculus problem and then extend it some new differential techniques when we need them. We're not trying to replace a course that you might get it as an undergraduate. We're not in a race to cover 12 to 15 techniques. We do a lot of modeling and just develop those techniques when we need them. This is a problem I chose because it really is one of my favorite problems. It doesn't take a high level of technique to solve. And I usually save this in North Carolina, we usually get about one snow day a year. So I usually save it for that snow day and let them work on it. But without further ado, I'll jump into this. If you have questions, please put it in the chat box or speak up. Let's go ahead. Here's the description. I did put this in the introduction to the problem. I am moving my screen around here. Snow starts to fall before noon and falls at a constant rate all day. At noon, a snowplow starts to clear the road, and the velocity of the snowplow is such that it plows a constant volume of snow per unit time. The plow goes 30 miles during the first hour and 15 miles during the second hour. And the question is simple: what time did it start snowing? Okay, so you can imagine there's a lot of information here, and maybe it doesn't seem like there's that much information. Maybe it seems like there's not enough to solve it. And that's kind of the beauty of this problem is it's kind of simply stated, and there's a lot of math that's kind of hidden in here that the kids have to kind of dig out. So again, I'll let you process it again for a second. Again, it starts to snow before noon and falls at a constant rate. So you can imagine that height just increasing at that constant rate. And then at noon, a snowplow starts to clear the road, and the velocity of the snowplow is such that it plows a constant volume per unit time. So obviously, as the snow gets deeper, it's got to slow down. It can't travel as fast because it's clearing the snow at a constant rate. It goes 30 miles during the first hour and then 15 miles during the second hour. Okay. Any questions before I go into any deeper into this? Any questions, clarifications, anything like that? Some people aren't quite sure where to begin, but let's go ahead and see what maybe we'll just kind of take it piece by piece here. So let's go ahead and look at our given information. We're told that we got to define some variables, right? We need some notation here. But what's given first is we're given a couple of constant rates. Snow is falling at a constant rate, and we're going to call that D for the depth of snow. So we're given that the rate of change of the depth is constant. We're going to call that K. All right. And then V, we're going to let be the volume of snow plowed, and that's going to be at a constant rate. So where V is the volume of snow that's being plowed. So therefore, dV dt is equal to some constant R, where again, V is the volume of snow that's plowed. So again, hopefully you have some context here. I grew up in New York, so snow plows were all over the place. In North Carolina, they rarely break them out. You might see one every couple of years, but let's see if we can start combining this to get a differential equation that we ultimately want to solve. So let's see if we can relate those rates together. How do we take our given information? And this is where the kids kind of struggle a little bit because there's a lot of information, but how do we take all that together and figure out ultimately what time it is when the snow level is at zero? So again, you can't just dive into that part of it, just figuring out the time. You got to kind of piece it together little by little. And then here's the other thing is, how do we relate the depth of the snow to the volume of snow plowed? And here's a little picture here I think might help you. So on the left here, that's a T star. I apologize for the font there. It's not great. T star is when the snow started falling, right? You can imagine that. Maybe it's 10 o'clock, maybe it's 9 o'clock, I'm not sure. At noon, that's our T equals 0. That's when the plow goes out. This big snow truck goes out and starts plowing. What we want to do is think about that little interval there, that change in T, right? Over some small time interval, what was the change in the volume of the snow that was being plowed? Okay, so just let's think about a small change in volume, right? Over that little time interval. So there's a few things that we have to take into account here. So the change in volume is, you think of this as kind of like a three-dimensional cube or a block of snow, if you will, where we have the depth, that's the height of the snow. We had the width, which is the width of the snowplow. And then our change in S is our change in distance over that small time interval. All right, so you can imagine that's how much volume, that's the volume of the snow that was pushed out of the way over that small time interval, right? You have the depth of it, which is relatively constant, right? It is changing, but over a small time interval, that depth is relatively the same height. We'll eventually shrink down that delta T, but getting ahead of ourselves. But approximately the volume that's being moved out during that small interval is the depth times the width times the length, which is our change in distance. Okay. Any questions? I know I'm going through this kind of quickly, but any questions so far? Any questions? This part's kind of critical, understanding this. So I'm going to give you about maybe a minute to process this and see if you have any questions. Right. So if we're looking at the change in S, right, that change in distance, that will eventually be that'll be our speed of the truck, if you will, right? We'll get to that piece in a second. Good, nice observation. All right, because we don't really have a differential equation yet. And there was one other thing I was going to say here. Yeah, okay. Well, I think we can keep going. So again, W is the width of the plow, and change in S is the distance traveled, as I mentioned. Okay, so now we're going to take that same equation and divide both sides by delta T. And again, it's approximately equal to that, right? But we're just dividing the both sides by delta T. And you can start to see this, this average rate of change, right? The change in volume with respect to time. And that's where that kind of change in S over change in T. Now we're starting to think about the, actually a speed of the truck right now. And then we take the limit as delta T goes to 0, and we get this beautiful differential equation, right? So the rate at which the volume is being removed per unit time is the height. And again, this is instantaneous, right? So it's the height at that time T times the width of the snowplow times the speed of the truck. Okay. So there's our differential equation. But remember, what is dV dt? dV dt is a constant, right? So that actually, we needed that to kind of build up this equation, but we know that's just going to be a constant. So let's simplify our dE, differential equation. And we know that the rate of change of the depth is K, right? Let me go back to this equation just for a second. We have D of T in there. We'd like to get rid of that, right? And we know the depth is changing at a constant rate. So maybe we can change that out. If we know what the depth is changing at a constant rate, then we know D of T is going to be a linear function, right? Again, nothing. And what's great about this is what I was going to say before. What's great about this problem is it doesn't really require any high level mathematics. It's just a lot of the things they learned in a basic single variable calculus course. And it's just kind of putting all those pieces together. There's not any, this isn't a couple differential equation. We're not looking at second order DEs, non-homogeneous, none of that stuff. And that's why I kind of like it for a snow day, because you can put it in their hands. Sometimes I give them a little scaffolding to kind of give them some hints, but sometimes I just let the kids just see what they can do with it. And you'd be surprised. Some kids actually can work this out. Well, let's see if we can simplify our differential equation. So again, the rate at which the snow is falling, the D is the depth, right, is a constant K. So we know that the depth of the snow at any time T is going to be K times T plus C. And again, what are we trying to find? What's the original problem here? If you recall, we're trying to figure out when the depth of the snow is equal to 0. Okay. And C is K is the rate at which it falls, and C is the depth of the snow at noon, because remember, again, we're considering T equals 0 when the snow plow goes out. But again, we want to figure out the time T star where the depth was 0. That's the whole goal of the problem, is what time did it start snowing, right? T equals 0, that's noon. And C is the height at that point. Okay, And you can see here, we can easily solve for T star here. When I plug, when I set it equal to 0, I get T equal to negative C over K. Now, just kind of keep that in mind. We'll see that again later on. That's what we're looking for. If we can solve for C and K, we're done with the problem. All right, let's see if we can get there. Let's see what our differential equation simplifies down to. So dv dt, that was what we left off with, is equal to the depth times the width times the speed. And again, dv dt, that's the rate at which the snow is being plowed. That's a constant rate. That's r, right? Again, the deeper the snow, the slower the snowplow truck can go. So therefore, that's where you can think of that r value. That's constant. We just calculated d of t. The depth is a linear function. So that's kt plus c. Again, if we can figure out what k and c are, we're done, right? That's the goal. We have the width that doesn't change. And do we have ds dt? And now we can solve for ds dt and we get this wonderful differential equation, which is now seems like we can sink our teeth into. All right, so let's see. What's the only piece of information we haven't really used yet? I'll wait a second, see if anybody can jump in there. What haven't we used yet? Chat here. Feel free to put in the chat box or speak up. What haven't we used yet? I know it's late on a Friday night. I appreciate y'all coming. What haven't we used yet? There we go. How far the plow goes in the first hour? Yeah, no, you got it. Yeah, they traveled 30 miles in the first hour and then 15 miles in the second hour. That's what we haven't used yet. Okay, so let's see if we can incorporate that. Excellent. And there we have it. The plow goes 30 miles during the first hour and 15 during the second hour. So that seemed like a big piece of I mean, that took up most of the problem statement, and we haven't even used it yet, right? I mean, that was like the second half of it was about how the plow was traveling. So let's see here. We know ds dt equals r over kt plus c times w, and ds dt is our velocity function. So we know our position at t equals 1 after 1 hour. S of 1 is 30. So we can turn this into a nice integral. And we start plowing at noon. So from 0 to t equals 0 to t equals 1, the change in position is 30. So here we go. So S of 1, which is equal to the distance traveled over that first hour, is just the integral from 0 to 1 of ds dt, right? That's if I integrate my velocity, I'm going to get my distance traveled. I pull the 1 over w out front. That's just a constant. And I changed to x here. I could have left it as t, but students are more comfortable with x, so put that in there. But you could leave that as t. And again, what is our change in our distance traveled over that first hour? That's given to be 30. Okay. All right, and this is a pretty easy antiderivative. It's just a natural log. Here it is. Slide this over on my screen. Okay. And you can see there, when I anti-differentiate this, I get the r over wk. Remember, r is a constant. I could have pulled that out front as well. I get this extra factor I get a 1 over k when I anti-differentiate that. But you get this, that's fairly straightforward to calculate. R over wk times the natural log of kx plus c, integrated from 0 to 1. And we know that's equal to 30. Slide this thing up. So we know 30 is equal to r over wk. ln, when I plug 1 into this, I just get ln of k plus c. And when I plug 0 in, I just get ln of c. And I'm subtracting these two. So with my properties of logs, I get ln of k plus c minus ln of c. And obviously, I can combine that into just one expression here. So I get ln of k plus c over c. And this I can simplify down. I got a c over c, which is just 1, and then a k over c. So I got r over wk equals times ln of 1 plus k over c, and that equals 30. And now you should start to be thinking, oh, this is kind of looks like that t star. Remember t star was something like negative c over k or negative, so we'll come back to that part, right? So we'll get back to that. So that's the first piece. And there it is. T star is negative c over k. So we're kind of getting close to that. So now we can actually introduce that into our equation, right? So we have 1 plus k over c. So I can get rid of that and just make that minus 1 over t star, okay? And we know this is equal to 30. And that's what we want to solve for, is that T star, right? K over C. So we change that to -1 over T star. So let's keep going. Now, this is one little trick here. The second hour, it traveled 15 miles, but we always like to have one of our bounds on the integral to be 0. So we're, instead of doing 1 to 2, going from t equals 1 to t equals 2 to be 15, we're going to go from 0 to 2 and make that 45 miles. It's a nice little algebraic shortcut. It simplifies things a little bit. So we're going to look at S of 2, the position after 2 hours. And again, we're going to integrate our speed function. And we know, very similar, this is going to equal 45 now. And I didn't show every step here, but when you anti-differentiate and plug in 2 and 0, instead of just getting k plus c over c, this time we get the 2k because we have a 2 up there. And again, making that substitution here, the c over c is 1, and then 2k over c ultimately becomes -2 over t star, similar substitution that we had before. Okay, so now we have two equations that have T star in them. So let's take a look at them. So solving for T star by, now we want to combine the two equations. Here they are. So the top equation is the one it's equal to 45. And the bottom one is what the one was equal to 30. So obviously that's equal to just 3 halves. So now you can start to see here, if we cross multiply this, well, you don't even have to cross multiply. We will in a second, but you notice the C is gone. That's not even in the problem anymore. The R, W, and K, those all cancel out. Those are all arbitrary, right? R is the rate at which we're plowing the snow. That's arbitrary. That could be a really large rate or a small rate. W, the width of the snowplow, that's arbitrary. That didn't come into play at all. K was the rate at which the snow was falling. That's arbitrary as well. It could be anything. So those things all drop out beautifully, and we're left with just this. When we cross multiply, we're left with this really nice equation that we want to solve for T star. And we're going to use some properties of logs again, almost to the end here. I'm going to raise this 3 up to the top, the 2 up to the top, and then exponentiate. That's what we call it here, canceling off those natural logs. And you get this really nice equation. You get 1 minus 1 over T star cubed equals 1 minus T over T star squared. Anybody want to take a stab at what, before we actually solve for T star, what they think the answer is? Anybody think sometimes I get really some clever people who kind of just figure out T star right from this equation. It's a special number, but all right, we'll continue. All right, so let's go ahead and expand this. So we're going to expand it. We're going to get rid of that T star just for now, because just for ease of notation. All right, so you got to remember when you see T here, that's really T star, but it gets messy with all those exponents. So I cubed the left-hand side, I squared the right-hand side. And now I'm going to kind of combine this thing. I'm going to multiply the left-hand side. Well, let's see, the 1's cancel off, and then I'm going to multiply both sides by T cubed. I actually don't think I need to do that yet. Let me subtract the 1, and then I'm going to swing everything over to the left-hand side. So 4 over T minus 3 over T is 1 over T. Then I have the 4 over T squared. When I bring that over, that becomes -1 over T squared. And then I still have the -1 over T cubed there, set equal to 0. And now I want to multiply both sides by T cubed. And I get T squared minus T minus 1 equals 0. Anybody recognize it yet? Sure, if anybody. I know it's late on a Friday night. But when we solve this thing, and again, that was our T star, that's what we're looking for, we get the golden ratio. Again, it just pops up in a lot of places. We get 1 plus or minus the square root of 5 over 2. All right, so we're pretty much done. Well, let's just kind of finish it off now. So which value do we choose? Well, T star needs to be negative because T equals 0 was noon, right? We want to figure out how much before noon it started to snow. So we're going to go with a -1, 1 minus the square root of 5 over 2, which gives us -0.618, which again, this is all in terms of hours. So now I need to convert it to minutes. So multiplying by 60, I get basically 37 minutes or -37 minutes. So therefore we get, it started to snow at about 11:23. Okay. So kind of if you think about this problem, it's doesn't have there's not a lot of complexity to it. It's just a lot of different pieces that just you got to figure out how they fit together. And there's a lot of letters. There's not a lot of numbers in it. So students can get a little tripped up with all those parameters and constants and things like that. But you can see the calculus that was involved is pretty minimal. It's a beautiful differential equation. And what I love about it is you see all those things are all those constants just drop out, right? The width of the snowplow, does that even matter? No. Does the speed at which the snowplow travels matter? No, that doesn't matter. The depth of the snow, at the rate of that falls, that doesn't matter. So all these things are really just arbitrary constants, and they don't really affect the answer at all. But there it is. So